In this next module, I'm going to give you some strategies for dealing with repeated events. So up until now, we've been dealing with the situation where we were just modeling the time until the first event. And that makes perfect sense in the context of survival analysis. Remember that these methods were developed around survival. Since death presumably can only happen once, the survival analysis methods really were kind of first modeled around time to first event. However, there are lots of binary events that could repeat during the time course of a single study. So for example, if you're looking at fractures, women or men could have multiple fractures during a study, or heart attacks. People could have multiple heart attacks, or depression episodes, or disability episodes, or pregnancies. Depending on how long you're following people, all of those things could repeat a number of times across many subjects. How do we deal with those repeated events? So there's a bunch of ways that people have come up with for dealing with repeated events. I'm going to go over basically 3 of the main strategies that are used to handle them. So separate models, counting process models, and conditional models. I'll go over each one of these in turn. Just to have a little tiny data set to work with here, here's a very small example data set. It only has 2 subjects in it, but it'll give you a sense of how the data would be structured. So for example, there's subject number 1, ID number 1, has 3 observations in this data set because that person started the study and then 5 months into the study they had the event, whatever the event is here. But then we allowed them to continue in the study. We didn't stop them, end them at the time of event. We allow them to continue in the study. The next interval of interest starts at 5, and from 5 on, they then again have another event at 25 months into the study. And then we start the clock again at 25 months, and from 25 months till the end of the study, which occurred at 36 months, they did not have another event, so they're just censored at the end of the study. Subject 2, again, has multiple observations because they had multiple events. So they had an event at 19 months into the study, and then again at 25 months, and then at 29 months, and they were finally censored at 36 months when the study actually ended. These are made-up data, but this was what a real data set might look like. So the first strategy, in a way, is just the simplest strategy that you could think of. So one strategy would be simply to run a new Cox regression model every time you get to a new set of events. So you could run a Cox regression model up until the time to first event for everybody, and then you could run a whole separate model among everybody who had a first event. You could then do a new Cox regression that represents their time to the second event. And then if enough people had a second event, you could again run a Cox regression model that looked at just the data of everybody who had a second event up until the time that they had a third event, and so on. So you can repeat this as many times as you need to. Now, of course, the obvious problem with this strategy is that, well, first of all, you're running separate models. So you're going to get separate betas for the time to first event, time to second event, time to third event, etc. Now, that might be legitimate if, in fact, the risk factors for having a first event differ from the risk factors for having a second event. So you can imagine for something like a heart attack, perhaps the risk factors for having a first heart attack could be different for the risk factors for having a second heart attack. So it might make sense if you're dealing with something where those risk factors could be very different. Of course, the problem here is that you're going to get increasingly smaller and smaller sample sizes. So your risk set, after you run the first model, your risk set is then only people who had a first event. And that might be only a small number of people. Or if you keep going, eventually, at some event, the 4th, the 5th, you're going to have too few people to run another model. But let me just show you what this would look like in terms of the likelihood function. It's going to be very simple because, again, we would just run separate models. So we would sort of have Cox model 1, and we would do a likelihood for that. So that's going to be up the time until the first event. So we're going to have 2 events in this model. So both subject 1 and subject 2 had an event. So subject 1 had an event at 5 months into the study. So at that time, I don't know what the predictor is here. Let's just call it X1 for subject 1, whatever their value is for weight or blood pressure or smoking, whatever X is. So they're the one who had the event at 5 months into the study. Who was at risk at 5 months into the study? Well, both subject 1 and subject 2 were at risk. So they each get a term in the model. At 19 months into the study, subject 2 had an event. Well, because there's only 2 people here, subject 2 was the only person at risk, so that would actually go to 1. But the likelihood would look like that. Cox model 2, the second model, would take now and look at the time from the first event to the second event. So for example, subject 1, you would now start a new model where you'd count their baseline as the 5 months into the study is their kind of new baseline, and then they would end at 20 months into the study. So you kind of start the clock over again, and now they have a second event 20 months after they had the first event. Subject 2 has their second event 6 months after they had their first event. So subject 2 actually has an event before subject 1 in this schematic. So the likelihood term would contain a term for event 6 months into the study now. So 6 months since the first event. Person 2 would be in the numerator here for the first term in the likelihood, and both of them are at risk at that time, and then there's only one person at risk for the second event. So that just looks like that. So that's the idea of totally separate models, starting the clock for every new event. That, of course, doesn't in any way use all the data at once. So a strategy that would use all the data at once, that would come up with a single beta rather than multiple betas, the sort of the simplest strategy that uses all the data at once, is to do what's called a counting process model. You allow the subjects to contribute multiple observations in the data. So each person is at risk as long as they're observed in the study, even if they've already had an event. Up until now, the moment somebody had an event, they were sort of out of the risk set. They were dropped from the risk set. But now we're allowing people to recur in the risk set, to recur in those denominators in the likelihood function. They can occur in the partial likelihood function in the numerator multiple times. The problem that this brings up is that we are now counting the same person multiple times as if they were independent people. And so we've got a problem where we no longer have independence of observations. But we can correct for that fairly simply. We can correct for those correlations within person using those robust standard errors that I talked about earlier. So that's fairly easy to correct for. So the counting process model, what would that look like in terms of the likelihood? So in the counting process model, what we're doing, here's subject 1, here's subject 2, here's time, and here's, say, 5 months into the study, 19 months into the study. So person 1 is in the study. They have the events at 5 months, 25 months. So 25 months would be out here. So they have an event here, and they have an event here, and then they're censored 36 months into the study. Subject 2, on the other hand, they were also censored at 36, but they have an event at 19 months, and then again at 25 months, and then again at 29 months. So they have 3 events in the study. How would the likelihood term be set up? Well, every time there's an event, we're going to have a new term in the likelihood. So in this case, we're going to have 1, 2, 3, 4, 5 terms in the likelihood. The first term in the likelihood happens at the first event time, which is 5 months into the study. At 5 months into the study, there are 2 people at risk. So subject 1 and subject 2, they're both in the denominator, and subject 1 is the one who had the event, so they'd go in the numerator. At 19 months into the study, the next event occurs. That event occurs in subject 2, so we get something that looks like this. Notice that, again, people are repeating, so we have to account for that correlation with those robust standard error estimates. At 25 months into the study, we have both subject 1 and subject 2 are having the event. We'd have to put in the likelihood account for ties. We'd have to do one of those methods for accounting for ties. But we'd again have another term in the likelihood which would allow both of those, both subject 1 and subject 2 to have the event. And then the final term in the likelihood, again, everybody is at risk. Everybody remains at risk through the whole study period, at least up until as long as we're following them. So that's the idea of the counting process model. You'd come up with a single beta that represented the effect of whatever the predictor is here. Okay, yet another strategy. So there's one called the conditional model. The conditional model is actually very similar to the counting process model. So we're going to count people multiple times. They're going to be allowed to reappear in the risk set even after they've had an event. However, we're going to do one additional thing in the conditional model, which is we're going to stratify on which event number you're on, so that we're only comparing people who are on their first event to other people who are on their first event. We're only comparing people who are on their second event to other people who are on their second event. This recognizes the fact that the baseline hazard for the first event is probably different, or could be different, from the baseline hazard for the second event. So once you've had a heart attack already, your risk of having your first heart attack may be very different than your risk for having a second heart attack. Once you've had a first heart attack, possibly your baseline hazard for heart attack goes up. And so we want to compare only people who are on the same event number. So we're going to stratify. That's easy to do in the Cox regression model because we can do that stratification that I talked about last week. We can stratify on which event number you're on. And the way, again, since we're having multiple people recur in the data set here, we have correlations. We're going to correct for those correlations in our data using the robust standard errors again. Now there's two variations of the model. There's kind of two different ways of counting time in this model. So I'll show you both ways. You can see both ways in the literature. You can just count time from baseline, the way we did in the counting process model. Or you can restart the clock every time there's a new event and count time since last event. And I'll show you the difference of those. The easiest way, again, to see the difference is to draw out the picture and see how that's reflected in the likelihood function. So if I choose time since baseline, what's my picture again? So again, my picture here, here's subject 1, here's subject 2, here's 36 months when both are censored. And we're counting time since baseline now, so it's basically the same picture we had before. Here's an event happening here, another event, and something looks like that. What's the likelihood function going to look like here then? So now we are stratifying on which event you're on. So it's kind of probably helpful if we actually add to our data set the strata number, the event number that you're on. So just to keep track here, so this is the first event. This person is on the first event. Now they're on the second event. Now they would be on the third event. They were at risk for the third event. Person 2 is at risk for the first event, and then at risk for the second event, and then the third. And then they are at risk for a fourth event because they actually have 3 events. So we can add, we'd have to add a variable in the model that reflected which event you're on, which event number you're on. What's the likelihood going to look like though? So again, we're only going to compare people who are on event 1 to other people who are on event 1. So when the first event happens at 5 months into the study, both subject 1 and subject 2 are both at risk for having their first event. So they are both going to be included in the denominator here. The one who has the event, of course, is subject 1, so they're in the numerator. Now we go and look at the next event that occurs. So the next event that occurs at 19 months. Subject 1 is at risk for their second event at that time, but subject 2 is at risk for their first event. So in fact, because this is such a small data set that we don't have anybody else in the risk set, so the only person at risk is subject 2 for their first event, and subject 2 has an event at 19 months. So subject 1 is not included in the denominator now at this event at 19 months because this is stratified on event number. So this is a first event strata, this is a first event strata. All right, now we get to the second event. Now they're both at risk for the second event. So the next events that occur are at 25 months into the study. And just to make this simple, let's say we had measured it a little bit more finely just to make this easy. Let's say subject 1 has the event at 25.0 months and subject 2 has the event at 25.1 months, so we don't have to deal with ties. So now we're on a strata for the second event. The next event that occurs is at 25 months into the study. Subject 1 has the event. Both subject 1 and subject 2 are at risk of having the event at that time. So the likelihood term would look like that. Now, however, when the next second event occurs in subject 2, because I've jiggered the time a little bit here in this, let's say we know for sure that the second event happened second in subject 2. Well, at the time they had their second event, the subject 1 was no longer at risk of the second event, so the likelihood term would look like that, and so on. So you get the idea. We're stratifying on event time. So a slightly different way of running the conditional model is to, instead of counting time from baseline, is to count the time since the last event. And I've started to draw it here to show you the slight difference here. So if we count the time since last event, we restart the clock every time a person joins a new event strata. And again, it's good probably here to put a strata for the event number, which number event people are on. That's like a new variable in my data set. So for event 1, person 1 is at risk for event 1 from 0 to 5 months into the study, and person 2 has their first event 19 months into the study. Then we restart the clock. So now it actually takes 20 months for the first person, for subject 1, to have the event again. So we start the clock again at 0, and they have their second event at 20 months. Subject 2 here if we restart the clock at 19 months, only took 6 months to arrive at to have their second event. So that would be slightly different in the likelihood then, because if you think about the likelihood now, the terms for event 1 actually are going to look the same as before. So we have a term where subject 1 has the event, both subjects are at risk at 5 months, we multiply that by only subject 2 is at risk at 19 months. Then we get terms in likelihood for the second event time. Again, we're stratified on event time here. But now the first person to have an event is subject 2 because they have that event only 6 months later. And remember, I kind of said, let's pretend that subject 1 had an event at 25.1 months and subject 2 had the event at 25 months so that we could say subject 1 was second in having the event. Well, now because we restarted the clock and subject 2 had a second event faster, they get the first term in the likelihood. So their term, now they're going to be in the numerator of the risk. You can see how that changes the likelihood function. So like that. And then subject 1 gets the next term in the likelihood. And of course, only the simple data set, they were the only ones at risk. And then we keep going with event 3 and event 4, etc. So you can see how that slightly changes the likelihood to count time since last event. And you'll get slightly different answers depending on how you count time, depending on the situation. You may prefer conceptually one over the other. So those are several different methods for handling repeated events. So now I'm just going to show you an example from the literature where they had a repeated event and they tried modeling it with several of these different strategies to compare them. So here's what the data look like. They drew a nice little graphic of their data. The event here was disability, and obviously episodes of disability are something that can repeat. What you're seeing on the graph here is that, for example, this first person didn't have any episodes of disability, but they died somewhere during the study. Subject 2, right here, never had any episodes of disability. Subject 3 had a bout of disability starting at about 69, looks like about 69 months into the study. And this whole thing here is considered a one episode of disability, all these dots. So every essentially month they're having disability, those kind of run together into one episode. Subject 4 has an episode of disability that lasts from about 12 to about 13 months, or maybe 11 to 13 months. They have a repeated episode of disability later on in the study. And subject 5 has 1, 2, 3, 4 bouts of disability. And this was a much larger data set, so this is just 5 subjects pictured out of a much larger data set. The authors were actually nice to show the actual structure of the data. What does it look like in the data set? That can often be very useful. And they were trying to illustrate the principle of how to apply some of these different strategies. So they shared their data structure. So this data set here that you see corresponds to the picture on the previous slide. So subjects 1, 2, and 3 don't repeat, but subject 4 has multiple observations in the data set because they had multiple bouts of disability. Same with subject 5. The start and end time shows you the time from baseline to, for subject 1, they died at 20 months into the study, so they were censored then. The interval represents which event number are they on. They only were at risk for one event, the first event. They never had a first event. This is the total time in this interval. The number of previous events here was 0, and the predictor we're going to care about is gender here. So 0 means that they were a male, 1 is female. So let's go down to one of the more interesting ones. So subject 4, who repeats, they start the study, 0 is baseline. 10 months into the study, they have an event. So that's interval 1 because that's when they were at risk for the first event. That interval, the time in that interval they spent in that interval was 10 months, and this person is a female. They've had 0 previous events at that point. Their next interval, they have a bout of disability that actually lasts from about 10 to 14 months. So they're next at risk for having disability. Once they get out of that particular episode of disability, they're again at risk of disability from 14 months, and then at 46 months they have an event. That's the second interval because that's the time period at which they were at risk for a second bout of disability. That time interval lasted 32 months from 14 months to 46 months. Now they've had 1 previous event and they're still female. And then The last thing that happened was they became at risk again. Their second bout of disability stopped at 53 months. They became at risk again, and then 72 months into the study, the study ended and they were censored. So that has a value of censored. That's their third interval. That third interval lasted 19 months before they were censored. At that point, they were on their third event, so they were at risk for this sort of third event, so they'd already had 2 previous events, and of course, they're still female. That's the data structure, how they set it up. And then they ran a bunch of different models looking at the outcome of either bathing disability, episodes of bathing disability, or other disability other than bathing disability. And they looked at one particular predictor, which was gender. So they compare women versus men. They're going to get hazard ratios for the risk of disability for women versus men. They used a whole bunch of different models to show what happens if you handle the repeated events in slightly different ways. And in fact, there were more models than I'm showing in this table. I've compacted this table just to focus on the ones that we've talked about in this module. They went into other types of models as well, but this is the ones that are relevant to this module. They ran a Cox regression model where they just did the time to the first disability event, and they compared again women to men. So that's this result right here. So what you'll see is that the hazard ratio that they came up with if they compared women versus men for time to first event is that the women had a 30% higher rate of the time to first bathing disability. However, for other disabilities, it was fairly null. There didn't seem to be a gender difference. So that's ignoring all of the stuff that happened after that first bout of disability, which is a lot to ignore. They then ran the Cox regression model incorporating the repeated events in a number of different ways. So they did the counting process model, which I talked about. They then did a modified version of the counting process model. What they've done here is they've adjusted for the number of previous events. So they adjusted for this previous events variable. They just put it in the model as another covariate. Now, the one thing that happens when you do that is you are assuming proportional hazards here. But it, in a way, is very similar to stratifying on the event number, which is what the conditional models do. So they adjusted rather than stratified for the event number, and that's what you're seeing on the second row here. And then they did the 2 different conditional models, counting time since baseline and counting time since last event. And what you can see is that in the first counting process model, where they didn't adjust for which event you were on, for event number, they did get a slightly higher hazard ratio for men versus women for bathing. But for other disability, that was very similar to some of the other ones you're seeing here. When they adjust for event number, you get hazard ratios of 1.37 and 1.39. And then for the conditional models, you're getting hazard ratios in that ballpark. So for conditional model A, when we stratify an event number, we get a hazard ratio of 1.35 and a slightly lower for other disability of 1.25. And when you do time since last event, it attenuates just a little bit, 1.27 and 1.18. But you can see that they're all relatively within the same ballpark. The time to first event model actually gets a pretty similar answer for bathing disabilities, but it gets a very different answer for other disabilities. All of the other ways of handling repeated events were significant or very close to significant, with women having a higher rate of disability than men. That wasn't true when we just did time to first event. So you kind of missed something if you did only time to first event on the other disability outcome. So again, those are a couple of different ways to handle repeated events in your Cox regression model.